Welcome to this course which is entitled Electromagnetic Field Theory. Now, electromagnetic fields or electromagnetic waves as such, the name is not very new to us. This is something that we have faced earlier at different levels in our high school physics, perhaps starting from as early as 8th grade. Now, waves as such, they can be, the examples of waves are waves on a water, the waves in the ocean, sound waves, light waves, so on and so forth. Now, from our high school physics, we know that as far as the different kinds of waves are concerned, there are two broad classifications. One is what we call as longitudinal waves. The other is called as transverse waves. So the classic example of longitudinal wave is a sound wave, wherein the energy of the wave propagates by making the particles in the particles in the medium vibrate. That's the way sound waves travel. So when we say something in air, the sound waves essentially make the air particles vibrate, thereby they move. So it goes without saying that if there are no particles, the energy cannot propagate. So therefore longitudinal waves need a medium to propagate. Transverse waves on the other side, or on the other hand, depending on what kind of transverse wave it is. For example, light. As we all know, the wave nature of light allows it to travel across any medium, including vacuum. So we know that light can travel in almost any medium as long as it is transparent. The only thing that changes is the velocity of light. Now, electromagnetic waves are a very broad term. That is to say, it's not just light. So, by the name, you can guess that all electromagnetic waves have two components, an electric component and a magnetic component. And essentially, these components make up the wave. So, unlike many different areas in physics that we have learned, for example, mechanics, optics using light, and so on, these kind of areas in physics, for example, mechanics, motion, is something that we can see through our eyes. Light is something we can see through our eyes. But then again, these electric and magnetic components are not visible to our eye. Moreover, light is just one example of the electromagnetic wave. There are several different types. So you may know this, that electromagnetic waves consist of very high frequency waves, including gamma rays, down until radio waves, which are the lowest frequency. So light comes somewhere in the middle. Gamma rays are used in radiotherapy, in radiation studies, whereas radio waves are essentially used in communications. So just to name a few others, starting from gamma rays, you have X-rays, you have ultraviolet rays, then you have what we know as the visible light, then infrared, then we have a broad spectrum of microwaves, and then finally radio waves. So radio waves and microwaves are those waves in which most of modern electronic communications take place. If you pick up your mobile phone and make a call, a microwave essentially gets transmitted and received. Whether it is to talk to a satellite or receive a GPS signal, whether it's a Wi-Fi signal or the walkie-talkies that our security and policemen use, all of these make use of radio waves and microwaves. The broad thing that I'm trying to say is that they are all electromagnetic waves. So when we make a call, the wireless signals that flow as waves, they are not visible to us. So therefore, the physics behind these waves and their components is not something that is immediately clear to us. So this is something that we shall look in this course. In this course, we shall attempt to understand this physics in a little bit more deeper manner. We shall try to understand this physics, understand how these electric and magnetic components are created, or how do they exist. Do all waves consist of electric and magnetic components, or the converse? Does having electric and magnetic components guarantee that an electromagnetic waves will always be there? We don't know. These are some questions which we shall try to answer in this course. We shall also see that what does it take to make a wave travel from one place to another. I kind of gave you a hint, or rather I kind of made a very strong statement sometime a few minutes back that electromagnetic waves do not really need a medium to travel. But can we make them travel the way we want? So we shall definitely try to answer some of these questions. So all said and done, you will know that when a ray of light passes from one point to the another, it travels in a straight line. However, that does not make the phenomena of light or the phenomena of the wave a one-dimensional phenomena. I can point a laser beam or a ray of light anywhere I want and it will travel in a straight line. So this tells us that even though we are used to the notion of rectilinear propagation of light, the phenomena of light or the phenomena of the wave is not necessarily a one-dimensional phenomena. I can have light travel on a three-dimensional axis or a three-dimensional coordinate system. It will still travel in a straight line, but in general it can be any 2 points on a 3D coordinate system. So say for example, I have this. Let's say this is my x-axis, this is my y-axis, this is my z-axis. I have a point over here, let us say this is A, which is x1, y1 and z1. And I have another point B, which is x2, y2 and z2. So in general, light can definitely travel. It may not look 100% straight, but it should be. So in general, it's a 3D phenomena. We shall try to look at this 3D phenomena a bit in this course. In fact, we shall be looking at it a lot, not just a bit. So again, these are some things which are not so easy to visualize because we cannot see them through our eye. The fields. We can see light, but then we cannot see radio waves. We cannot see gamma rays. We cannot see infrared. So that's the problem. So the question is, or rather the difficulty with this physics is, this is one thing. One is non-visibility, the other is a 3D. So this field, these waves, they exist in 3D and usually they are not something which we can easily visualize. So therefore, this is the inherent difficulty with these waves. Now, however, that did not stop the early researchers in this field from trying to understand this field. So a lot of experiments were done and a lot of phenomena were observed by the early scientists, particularly in the 19th century when this field was probably discovered the most and made the maximum number of strides. And ultimately this is what led to the invention of the system through which we can generate electricity for domestic purposes. We not just generate it, but also transfer it from one point to the other. Now, some of the minds or some of the names which come into our mind of scientists who delved into this area in those days include Michael Faraday. We all know Faraday's law of induction. Then also comes the experiments by Oersted and Ampere, which sort of proved the opposite, that just like how Faraday said, if you have a magnetic field, you can generate voltage out of it. Ampere and Oersted essentially proved the otherwise, that if you have a current, you will have a magnetic field around it. So the fact that static electric charges create electric field, as you very well know through Coulomb's law and similar things in physics, static charges give rise to electric field, whereas moving charges give rise to magnetic field. So there is a very subtle relation between the two. The origin of both electric and magnetic fields comes through charge. Only the nature of the charges change. But coming back to this 3D problem, fact that 3D and non-visibility make things a little difficult to study for us, especially those who are new to this field, what we shall do is, we shall essentially reduce the 3D problem into a 1D problem. Can we do this? Let's see how. I just mentioned that a current carrying conductor generates a magnetic field around it. This is something we all have learned in high school. So let's look at something that we already know. Let's have a source over here, and let's have a load, and let us connect them by means of two conductors. I shall come back to that current carrying conductor generates a magnetic field in a short while, but before that, let us try to understand this using theorems that we already know. And the easiest theorems are nothing but circuit theorems. Using circuit theorems, I can see that this is a circuit, it has a source, it has a load, and something as simple as using a pair of conductors to connect the source and the load. The question now is, let's suppose this source has a voltage Vs of t that is sinusoidal. Suppose that is some V0 cos omega 0 t. That's a function of time. Obviously, we all know that alternating currents or alternating signals are functions of time. So now, if the voltage across the source is Vs of t, what will be the voltage across the load? This is a no-brainer. Voltage across the source will be equal to the voltage across the load, because that's what Kirchhoff's law tells us. So, according to KVL, if this is, let us say, VL, then the load voltage VL is nothing but Vs of t, which is nothing but V0 cos omega 0 t. So that is something which we all know. Big deal. So why are we talking about these things? We already know this. Do we? Do we really know this? Are we forgetting something? Or rather, are we applying this KVL keeping some assumption in mind? The answer is yes. Let us look at the source a little bit more closely. I have said that the source is sinusoidal in nature. The source is sinusoidal in nature. That means if you draw this wave as a function of time, you're going to get this. And what is this? This is a wave. This is definitely a wave. It changes as a function of time, and it changes using the cos function. So therefore, Let us say at time t equal to 0, we are switching on this simple circuit. What essentially happens is that a wave starts from the source and moves along the positive x direction. If you assume this is the x-axis, the wave starts moving along the positive x direction because it is guided by this pair of conductors. So therefore, this wave essentially starts moving. We know that. Now, let's say let's suppose the wave velocity is v and the length of this line is L. Then the time taken for the wave to travel from the source to the load is what? Let's call this as the propagation time. That is Tp. So as you know, the time taken to move from one place to another place is nothing but the distance divided by the velocity. So in this case, displacement is the shortest path. So this is nothing but L by V. Is that right? Yes, it is. So, what next? Let's redraw this diagram. Source and load. So, at time t equal to 0, this source voltage is V0. So this V0 will start like this. Now this V0 will appear across the load after time Tp. So this wave will keep flowing like this, so on and so forth, until this becomes V0, the voltage across the load. Now, as we said, let's suppose this distance is L and this is the positive x-axis. So now this leads to an interesting premise. What can we say about the time and, or rather, how fast does the load voltage change? Or for example, this V0, after how much time does it appear over here? So the question is, longer the distance, more will be the time required for any change in the source voltage to reflect at the load voltage or the load end. So therefore, as the circuits become large, as circuits become larger and larger, what happens? It takes more time for the voltage to reflect. So now we see a very interesting phenomenon. Now the voltage at any point on this line, whether it's here or here, is not just a function of time anymore. It is a function of time as well as the position. Because now you can no longer neglect the length if it is very, very long. Because then there will be considerable time taken by the wave to travel from one point to the other. But as you know, electromagnetic waves in vacuum have a very high speed. They have a speed of about 3 into 10 raised to 8 meters per second. And so you will say, well, how long can the time be? The time will probably be a few milliseconds, nanoseconds, something of that kind. Well, that can create a lot of difference depending on the application. For high-speed applications, a 1 millisecond delay is disastrous. Now let us look at this same problem, but from another angle. Let us now consider the wavelength. How do you define wavelength? Wavelength corresponds to the physical distance over which the wave starts repeating itself, or after which the wave starts repeating itself. So in time domain, what we have as the time period of the wave. So for example, this is the time period, that is t. The distance is the wavelength lambda. Now, let's say we make lambda very small. When we are making lambda small, we are essentially reducing the time period also. Thereby, the frequency increases. So when we make lambda small, what happens is, even if my value of length is finite, take for example the circuits that you have used in your circuits lab and made them on the breadboard. What is the size of a breadboard? The length of a breadboard is at the most 15 to 20 centimeters, not more than that. So ask yourself, what is the frequency of the waves that you normally make them pass through the breadboard? Maybe 1 kilohertz, maybe 10 kilohertz. What's the wavelength? The wavelength of those waves are very large. Now I am saying, let us make the wavelength lambda very small. Beyond a point, it so happens that the wavelength becomes so small that it starts becoming comparable to the length of the breadboard or the length of the circuit. In this case, if lambda becomes very, very small and comparable, this may happen. This is when the wavelength becomes exactly equal to the length. This is a very special case, when the wavelength of the wave becomes exactly equal to the length of the conductors. Then in that case, can we say that whatever is the source voltage, the same will be the load voltage at any given point of time? We cannot say that. So let us say this is at time t equal to 0. Let's say at some other point of time it will be like this. So if we take a photograph of the wave, doesn't mean that I can see the wave, but supposing I were able to see the wave and I take a photograph of it, that means I am freezing time. If I am freezing time, can I still say that the source voltage will be equal to the load voltage? I cannot make any such claim. Well, in this case I can, because lambda is equal to L, but let's say lambda is more than L. Then can I make such claims? I cannot. I cannot make any such claim. So therefore, the moral of the story is, at high frequencies, that means small lambda. This is the first case which we just discussed, or the second case is when L becomes very large. L is the length of the conductor. At very high frequencies, when the wavelength becomes very small, or the L becomes very large. Either way, when L starts becoming comparable to the wavelength of the wave, oh, by the way, I forgot to mention, even if lambda is equal to L, at any given point of time, the voltages at all points along the line will change. So definitely we cannot say that the voltage will be a function of time only. It will be a function of space also, or position. So when L starts becoming comparable to the wavelength of the wave, that's lambda, the voltage or current become functions of time and position. This is very important. So therefore, the voltage V will be a function of distance x and t. Is that fine? Now, let us try to analyze this a little bit. Let's again have this source load configuration and say that a wave is flowing which is comparable to the wavelength. This is positive x-axis. So what we can see is that normally KCL and KVL don't hold. When voltage is a function of both time and position, KCL and KVL do not hold. Or rather, hold true. So then, what can we do? What can we do? As engineers, electrical or electronics engineers, all of us have some affinity towards KCL and KVL, and somehow we don't want to let it go. So the question is, can we do something in this setup and make KCL and KVL hold true? To understand that, let us consider what are the physical phenomena that are going on in the line. Suppose I have a pair of conductors which are very similar to this pair that is being used. So let us say current is flowing over here and coming back over here. Now what are the phenomena that happens? Now current flowing this way means some charges are flowing. These are conductors. In the ideal case, they will be very good conductors, so their resistance will be zero. But as we all know by now, no wire ever has zero resistance. Every piece of wire, no matter how good of a conductor it is, always has some small non-zero resistance. So therefore, the first phenomena that can happen is wire resistance. Now, what is the nature of this current? As you can see, the voltage is sinusoidal, so therefore the current will also be sinusoidal, or some version of it if the load is a normal load. So, what was the law stated by Ørsted and Ampere? That a current carrying conductor always generates a magnetic field around it. And if you recall, the direction of that magnetic field is the right hand thumb rule. If the current direction is my thumb, then the magnetic field direction is given by the way my fingers are curling, this way. So it's like saying both of these wires will generate some magnetic field. This both. Of course, they will be opposing, but that's a different story. Let us look at these two wires independently. If I have a DC current, then the nature of the magnetic field will be constant as a function of time. But since the signal that is traveling is an AC signal, the magnetic field that is generated will also be alternating in nature. That is called as Biot-Savart law that you may have studied in your high school physics because of a small current element. So now, if I have a time varying magnetic field because of a time varying current, that time varying magnetic field can also induce some voltage on these conductors or on each conductor. And what is that phenomena called? That phenomena is called as self-inductance. Self-inductance of wire. The third phenomena. have currents flowing in opposite directions. There are charges accumulated in the wire which are moving, and you have two conductors which are placed, let us say, not very far away from each other. Then because of charges at the two conductors which are in close proximity, you are definitely going to have some electric field between these two. If you remember, H is the symbol for magnetic field, E is the symbol for electric field. So if you have electric field between two conductors, what phenomena is that called? That is called as capacitance. The final phenomena, or the fourth phenomena that happens, is again due to the two conductors, or rather what lies between them. When I have two conductors, what lies between the two conductors? Generally air. Only these two wires are conducting. Between them is space or any insulating material. Converse to a conductor, an insulator should never conduct. So therefore, to model insulators which are non-ideal, just like you cannot have ideal conductors, you do not have ideal insulators also. No matter how good an insulator you have, it will always have some element of conductivity to it. So therefore, the fourth and final quantity is conductance between wires, or rather I should say of the medium. The first two, the wire resistance and self-inductance, they are due to the wires, even if you consider them independently. Capacitance comes because of the two wires in proximity, and conductance comes because of whatever is the material that is between the wires. How good of an insulator is it? That is conductance. So now we have taken some physical phenomena and sort of tried to represent it in terms of resistance, inductance, capacitance and whatnot, so that we can apply KCL and KVL. We are essentially representing physical phenomena in the form of circuit elements. So this is half the problem. The second half is how to apply the KCL and KVL on these. Now, suppose somebody gives you this pair of wires or this pair of conductors, which will be used to send a wave from one end to the other end. It is always better that we consider one small section on this wire. So let's suppose the wave goes something like this. We represent those four physical phenomena, that is resistance, inductance, capacitance and conductance. These four not just as a total phenomena, but as something that is distributed along the line. And this makes sense because magnetic fields does not exist at one point. In fact, they exist throughout. Here, here. The E fields exist throughout the length of the wire. They are not just limited to one spot. So therefore, rather than writing those four phenomena as single elements, we shall distribute them along the line. So we'll say represent each of the four phenomena using a distributed approach. When I say distributed, I mean as a function of length. So therefore we will say per unit length. Okay. Now, so that is like saying, so let's denote these quantities. R. R stands for wire resistance per unit length. So therefore the unit becomes ohm per meter. Inductance is per unit length. So it becomes Henry per meter. Likewise, capacitance and conductance, one is farad per meter, the other is mho per meter. Now, suppose a wave is flowing on this line from the left to the right. This is the positive x-axis. And I have taken a photograph of this wave at some time t. I don't really care what that time is. I just know that I have a snap of this wave at some instant of time when it looks like a stationary wave. Let us consider a very small portion of this line. Let's say this is delta x, where delta x tends to 0. It's a very infinitesimally small section of this line where we can say that the voltage change delta V is nearly 0, or the voltage can be considered almost as constant. That we can certainly assume. And then if we say that the voltage is nearly constant in this delta x, what that means? It means this delta x is so small that it is much smaller as compared to the wavelength. So therefore, if two ideal pair of conductors offer you non-changing voltage along its length, delta x, then we can definitely apply KCL and KVL on it. So, if we now magnify this and see what is inside, zoom in, we will see that we can represent these four phenomena in this manner. Resistance, inductance, capacitance, and conductance. The symbol for resistance and conductance is the same. Now, if you assume that the line has to terminate somewhere, if the current flowing this way comes back this side, we can definitely add the two resistances and the two inductors in series. We can definitely do that. Note that this entire thing is over a length of delta x. So what can we do? We can simply combine these two resistors, because whenever the line ends, this and this will be in series. So we can essentially make our life a little bit more simple by using these two resistances and these two inductors in series. So which will essentially make it like this. So since we have defined RLGC as per unit length quantities, this resistance will be R delta X, this will be L delta X, this will be C delta X, and this will be G delta X. Whereas this length is still delta X. So we'll pause here for the time being. So let's just quickly recap what we discussed today. We started the discussion from our knowledge of high school physics of electromagnetic waves. We took some examples also from the electromagnetic spectrum. And we said that, okay, all of these wave phenomena are nothing but 3D phenomena, and can we, just to make life simple, first convert this into a 1D phenomena. Because if you understand 1D, in my opinion, it sort of makes the analysis of 3D a little more easier. So we made it into a 1D problem by considering a wave that travels only in the plus x direction. We then established that when we apply KVL, we essentially use only time. We don't have any knowledge of position. But if the conditions are such that the time taken by the wave to travel from the source to the load is significant, and this can happen under two conditions. One is when the frequency becomes very high, that is the wavelength becomes very small, or when L becomes very large and starts becoming comparable to the wavelength. Then the voltages and currents become function of position as well as time, not just time. So therefore, KCL and KVL will not apply. But we wanted to apply KCL and KVL in some format. So therefore, we said that let us try to understand this physical phenomena on the line and try to model them using elements that we already know, that is circuit elements, RLGC. And this is precisely what we did. We took a small section of the line, an infinitesimally small section, where we assume that it is so small that the change in voltage can be considered to be minimum. So therefore, for this small region, the pair of lines act like ideal lines, so therefore KVL can be used. So we zoomed into this part of the line and we put those four physical quantities but as per unit length functions, and we saw that we can essentially denote the delta x version of the transmission line, or a delta x section of the transmission line, using these four elements. So by no means can this be considered as the full transmission line or the full line. By the way, the pair of lines which we use to send a signal from one end to the other end is called as a transmission line. So this is essentially the name of the topic that we are studying. We'll call this as transmission lines. So this section RLGC is only a representation of delta x section of the line, not the full line. The full line will have infinite number of such sections. So we shall pause here and continue in the next time.